In this lesson, we shall focus on physical optics, electromagnetic waves. Now, electromagnetic waves can be produced by accelerating charge. So by accelerating charge, we can be able to produce electromagnetic waves. Electromagnetic waves have electric and magnetic components perpendicular to each other. So speaking of what we call electromagnetic waves, they have both electric and magnetic components perpendicular to each other. Electromagnetic waves are transverse waves. Right, electromagnetic waves are transverse waves. Electric and magnetic components are perpendicular to the direction in which the wave travels. So you have that these electromagnetic waves are transverse waves, but electric and magnetic components are perpendicular to the direction in which the wave travels. Electromagnetic um, waves, right? So you have that. What we term electromagnetic waves can propagate through a medium. Speed of an electromagnetic wave in vacuum is 2.998 times 10 to the 8 meters per second. That is the speed of an electromagnetic wave in a vacuum, right? So we're then saying electromagnetic waves can propagate through a vacuum. They can propagate through vacuum. A couple of things are very important. So if you look at the y-axis, the x-axis together with the z-axis, this becomes what's called a three-dimensional space. But in figure 1, which is the figure here, representation of an electromagnetic wave, right, of an electromagnetic wave. So now, E and B are perpendicular to each other in the direction of propagation of the wave. So you can see that this one here becomes the electromagnetic wave. So if obviously at this point, as said here, I want to mention that we have the electric and the magnetic components. These being the electric component and that being the magnetic component, they are basically perpendicular to each other. And the actual as such that the direction of wave travel, right? So the wave travels, for instance, towards the right, but you can see the electric and the magnetic components are perpendicular to each other, right? So E and B, where E is electric and B is magnetic, are perpendicular to each other in the direction of propagation of the wave. So this diagram obviously shows that. I want us to look briefly at what we call polarization. Because electromagnetic waves are transverse waves, they can be polarized. Longitudinal waves cannot be polarized. So now the transverse waves can be polarized, but longitudinal waves cannot be polarized. But in electromagnetic waves such as the one depicted in figure 1, the electric field oscillates along the y-axis. Such a wave is said to be linearly polarized, with the direction of polarization taken to be along the y-axis by convention. An example of linearly polarized electromagnetic waves are those produced by straight wire antenna. Example of linearly polarized electromagnetic waves are those produced by straight wire antenna. For an electromagnetic wave such as the one depicted in figure 1, we saw the electric field. So this is the figure 1 where the electromagnetic wave has been shown with both electric and magnetic components perpendicular to each other and the direction of propagation of the wave. But now we're then saying for an electromagnetic wave such as the one depicted in figure 1, the electric field oscillates along the y-axis. So we can see that the electric field oscillates along the y-axis because this is the y-axis. So the electric field oscillates along the y-axis. This is the x-axis and that becomes a z. By convention, okay, your oscillates along the y-axis, such a wave is said to be linearly polarized, with the direction of polarization taken to be along the y-axis by convention. Direction of polarization is taken to be along the y-axis by convention. An example of linearly polarized electromagnetic waves are those produced by straight wire antenna. Those straight wire antenna the straight wire antenna produce what we call the linearly polarized waves. And now an example of linearly polarized waves are those produced by what you call straight wire antenna. The light given off by normal incandescent light bulb is unpolarized. So the light given off by a normal incandescent light bulb is unpolarized. So unpolarized light consists of many individual electromagnetic waves, each polarized in a random direction. See figure 2. Unpolarized light may be produced in a number of different ways. Unpolarized light may be produced in a number of different ways. When unpolarized light is passed through certain crystals of, for instance, the emergent light has vibrations in one direction only. So now, at this point, then you then say, the unpolarized light may be polarized, yeah? Okay, I want to start off this polarization of light. It's a very important discussion to have. Once again, obviously, because I want us to go through the exercises, we're not going to be very long on these, but I want us to pass through these so that when you watch the recording, you have a chance to understand. The light given off by normal incandescent light bulb is unpolarized. Right, so unpolarized light consists of many individual electromagnetic waves, each polarized in a random direction. Right, see figure 2. Shall look at that. So now, if light is unpolarized light consists of many individual electromagnetic waves, each polarized in a random direction. See figure 2. We shall look at the figure just now. But unpolarized light may be polarized in a number of different ways. When unpolarized light is passed through certain crystals, for instance, the emergent light has vibrations in one direction only. So there are many different ways. So in different ways, you can take unpolarized light and you can then begin to polarize it. But when the unpolarized light is passed through certain crystals, for instance, the emergent light has vibrations in one direction only. The emergent light has vibrations in one direction only. In one direction only. Okay, let us look at the following. Figure 2, for example, the direction of the electric field components for a polarized and unpolarized light wave. So we're looking at two forms of light wave. One is polarized and the other one is unpolarized. Now, the electric field in one direction. So you're able to see the electric field here in one direction there. But here you're able to see the electric field in the random directions. And now the direction of wave travel. Right, so if you see the electric field in one direction, if this is the direction of propagation of the wave, direction of the electric field component for polarized. So if we are to look at this one as being polarized, and this one being unpolarized, unpolarized. Okay, this one is polarized, and this one is unpolarized, light wave. This one is polarized, and this one is unpolarized. So the electric field in random directions. So you have this one in random directions in direction of wave travel. Polarization by reflection. Right, when light is reflected from from a non-metallic surface such as water, polarization by reflection. Let's discuss that one. So when light is reflected from a non-metallic surface such as water, it becomes partially polarized when the incident angle is greater than 0 degrees. When the reflected light makes an angle of 90 degrees with the refracted light, the reflected light is completely polarized parallel to the surface. See figure 3. Okay? When light is reflected from a non-metallic surface such as water, so you can have water and light can be reflected from a non-metallic surface such as water, it becomes partially polarized when the incident angle is greater than 0 degrees. When the reflected light makes an angle of 90 degrees with the refracted light, the reflected light is completely polarized parallel to the surface. We'll see figure 3. Now, the angle of incidence when this occurs is known as the Brewster angle. Right, so you have the ordinary unpolarized light. Here is ordinary unpolarized light, travels in this direction, and it strikes the surface. Unpolarized light incident at the Brouwer's angle, theta B, right, on a non-metallic surface is polarized parallel to the surface on reflection. Right, so now light polarized parallel to the surface. So here is light and it's now polarized right to the surface on reflection. So it is polarized. It is polarized now that it is reflected, but you're able to see that there's light that goes in there and that goes into the non-metallic surface. So the refractive index N. So now you have this angle here, which you call the angle phi, and also the angle theta b. There's the angle phi and the angle theta b. Okay. Now, I want us to discuss this. So now, Brouwer's angle is theta b. So the angle of incidence when it occurs is known as Brouwer's angle. Right, so you'd have a Brouwer's angle is theta b there. Okay, now there's something called the refractive angle, refractive index n, which is the sine of theta divided by the sine of phi. Right, now when BC is perpendicular to BD, when BC is perpendicular to BD, okay, so you're able to see that when BC, right, here is BC and BD, they're perpendicular to each other. The angle phi therefore becomes 90 degrees minus theta b. Hence, L becomes the sine of theta b divided by the sine of 90 degrees minus theta b. This is the sine of theta b divided by cosine of theta b, which is the tangent of theta b. Okay, let us look at example 2.1, polarization by reflection. Light is reflected from a glass coffee table. Light is reflected from a glass coffee table. Polarization by reflection. Light is reflected from a glass coffee table. When the angle of incidence is 56 degrees, the reflected light is fully polarized. Okay, here's a table, and we've seen that the light strikes like this, and then now is reflected like this, and then it is polarized. Right. Calculate the refractive index of the glass. Right, so we know that the refractive index of the glass is the tangent of theta, but not only tangent of theta, but n is the tangent of theta b. Right, now, when the angle of incidence is actually exactly 56 degrees, the reflected light is fully polarized. Because it's fully polarized, calculate the refractive index of glass. So you then say, obviously, this is going to be actually the same as you can write it as the theta b equals, or just theta is equal to theta b, right? And this can be seen as the theta of 56 degrees, which is 1.48. When the light is fully polarized, the angle of incidence equals Brouwer's angle. This is it. When light is fully polarized, the angle of incidence equals Brouwer's angle. So Brouwer's angle, obviously, as we saw before, is measured as the angle between the vertical and the reflected light, so the normal. So you have that this angle here is called Brouwer's angle. And obviously now you would relate that to the angle of incidence. Right, to reflect that, you relate that to the angle of incidence there. And therefore, when the angle of incidence equals Brouwer's angle, then we have this result. Let's discuss polarization by scattering. Light scattered by small particles is partially polarized. For example, so we're discussing first and foremost light scattered by small particles. Right, so there's light scattered by small particles. For example, light from the blue sky, which is scattered down to us by molecules in the atmosphere, is partially or is partly polarized. So some of the light that is from the sun through the atmosphere is polarized, but is partly polarized by the particles in the atmosphere. Right. There are some molecules in the atmosphere that those molecules that form the atmosphere, or there are parts of the atmosphere, but obviously, I mean, there's also dirt and debris in the atmosphere. Right. So now there's something we call the optical activity in 2.3. So now we discuss the polarization by scattering, and this happens when light scattered by small particles is partly polarized when this now hits some particles there, and it's partly polarized. It's partly polarized. It's partly polarized. It's partly polarized. Partly polarized. Okay. There's something called the optical activity. Some substances such as quartz or sugar solutions are able to rotate the plane of vibration of plane polarized light. For example, some liquids are made up of what we call the corkscrew like molecules, either of a light-handed or right-handed or left-handed type, and these correspondingly produce either a clockwise or anti-clockwise rotation as seen from the front. Such substances are said to be optically active. Optically active. So in the case of liquids, the amount of rotation is proportional to the concentration as well as the path length, as well as the path length. Thus, if theta is the amount of rotation, if theta is the amount of rotation, that's if theta is the amount of rotation, we have that theta itself is directly proportional to C times L, where C is the concentration and L is the path length. Right. So, and if theta is the amount of rotation, so the amount of rotation is the concentration times the path length. Usually theta is expressed in degrees and C in grams per cubic centimeter. Grams per cubic centimeter of solution, and L in decimeters. Thus, we're able to say theta itself is written as in terms of the concentration times the path length. Right, the concentration times the path length, where this theta in the square brackets is the specific rotation. So the theta can be written in terms of the specific rotation, where theta in brackets represents a specific rotation. And now the theta that is not in brackets is the amount of rotation. So the amount of rotation yields what you call the specific rotation multiplied by C times L. C times L. You have the specific rotation. So the amount of rotation, theta, is a specific rotation. Yeah, specific rotation times the concentration times the path length. Times the path length. Okay, we continue. Now, if you look at the example 2.2, the optical activity. The optical activity, the specific rotation of lactose is 52.3 degrees per square centimeter per gram. Um, the specific rotation of lactose is 52.3 degrees. Okay. Square centimeters per gram. Now determine the concentration of a sample contained in a 10 centimeter tube, right, which rotates plane polarized light by 60 degrees. Right, from the equation 2, we actually have some knowledge. We have seen that theta itself becomes the same as the following from the previous formula. So theta becomes theta C times CL. Theta C times CL. Okay, so that in the end, this is what we're getting. But we need to determine the concentration. So the concentration you divide, which is the theta CL. To get the concentration, you divide by the specific rotation times the path length. So if you do that, we divide also by the specific rotation times the path length. At this point, we're able to see that this one cancels. And this means that the concentration itself becomes theta divided by the specific rotation times the path length. Okay, now at this point, the angle theta becomes 60 degrees, plane polarized light by 60 degrees. And then you divide, you continue. And then you then say the specific rotation is 52.3 degrees square centimeters per gram. So the theta is a specific rotation, which is 52.3, but multiplied by the L, and that is the concentration itself. Okay, we did determine the concentration of a sample contained in a 10 centimeter tube. So the 10 centimeter tube is the path length, and therefore you divide everything and are able to get the answer, which is 0.11 grams per cubic centimeter. Okay, let's just discuss briefly the principle of linear superposition and interference. the principle of linear superposition and interference when several waves are present at the same place at the same time. So you're speaking about several waves present at the same place, but also at the same time. The resultant wave is the sum of the individual waves. So we speak about the resultant wave being the sum of the individual waves. For electromagnetic waves, the electric fields associated with the individual waves combine according to the principle of linear superposition. The interaction of individual waves with each other is known as interference. The interaction of individual waves with each other is known as interference. So you have constructive interference, and there's also destructive interference. Constructive interference, this is when the trough and the trough, the crest and the crest interfere with each other. And you can see that the trough and the trough will actually form a deeper one. And this one will form a much greater crest. The crest and the crest will form a much greater crest. And now increasing the amplitude. And therefore, there's constructive interference here that we were able to see because these are in phase, but these are certainly out of phase with each other because the crest and the trough here correspond, and therefore this leads to destructive interference. Now, figure 4, which is the figure we're looking at, but you can see the result is just a destructed wave, and now it's not a wave with a greater frequency there, a greater amplitude. Now, if you look at figure 4, yes, figure 4, when two waves of equal wavelength and amplitude are in phase, constructive interference occurs. When two waves of equal wavelength are in phase, right? When two waves of equal wavelength and amplitude are in phase, constructive interference occurs. So we're looking at equal wavelength and amplitude are in phase, constructive interference occurs. When waves are out of phase, if they are in phase, then there's constructive interference. When the waves are out of phase, as in the second diagram here, destructive interference takes place because they're out of phase. How do you see out of phase? You see the trough and the crest, and obviously this leads to destructive interference. If the trough and the trough correspond, the crest and the crest correspond, then it leads to constructive interference. Let's look at the next question or the next point. Consider two sources, source 1 and source 2, right? And now generating identical waves as depicted in figure 5. The solid curves represent wave crests, and the dashed curves wave troughs. This is it. So the solid curves represent wave crests. Wave crests, the solid ones. The solid ones. The solid ones. The solid ones. Right. Yes, we are told the solid curves represent wave crests, and the dashed curves wave troughs. So you have the troughs here, which are the dashed ones, and the solid ones are the crests. Along the lines where the solid curves from S1 interact with the solid lines from S2, constructive interference occurs. Likewise, along the lines where solid curves from S1 intersect with the dashed curves from S2, destructive interference occurs. So you look at the fact that at this point, likewise, so let us begin here, where we're saying along the lines where the solid curves from S1. So you have the solid curves from S1 intersect with the solid curves from S2. So now, if we were to look at these as S1, and you can see the solid curves from S1, right? Right. So you are looking at the solid curves from S1 intersect with the solid curves from S2. Right. There are also solid curves from S2 like this. And so constructive interference happens. Right. If you have this and you have these and they engage the solid ones, you have constructive interference. For example, let us see what is happening here. If this is that, and this one, right, and this one is a solid one from S1, and then it engages with a solid one from S2. And then we actually be able to see another solid that is formed, and therefore it is constructive. Okay, so now there's constructive interference, but now constructive interference occurs likewise along the lines where the solid curves from S1 intersect with the dashed curves from S2. So if this is S1 and you have the solid ones, but they engage with the dashed ones from S2, right? So if you actually check that very carefully, here are the dashed, the dashed from S2 for let me see this dashed one. So here's the dashed one from S2. Take a look at this one, the dashed one from S2. Let's look at the solid ones from S1. Right, because if this is S2, these are the dashed ones. Dashed, 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 dashed. So these are the dashed ones from S2. And then now you look at S1, it's producing some solids. And now you'd have another solid here. And then you'd have another solid there. And then now, if this is the dashed, right, and this is the dashed, and this is the dashed, for instance, from S2, and it engages with a solid from S1, what we're able to see is surely destructive interference. Right. So now, destructive interference then occurs, and we can study the patterns. But I want us to look at these symbols here. Now, if you have dashed and solid, dashed and solid, then there is destructive. Solid. So now at this point, you have dashed and dashed, constructive. Constructive. Here you have dashed and solid, destructive. Okay, then you have dashed and dashed, solid and solid is constructive, and so on and so forth. The two identical sources, S1 and S2, produce waves that interfere constructively along the lines marked C for constructive and destructively along the lines that marked. So this is destructive, that is constructive, and we've already discussed that. And move on to the next thing. Now, the drawing alongside depicts two sources, S1 and S2, generating identical light waves. The waves interfere at a point P. 。 on a screen at a distance x from the plane of the two sources. Constructive interference occurs at P when the waves from S1 and S2 are in step, which happens whenever the difference in path length, which is S2P, S2P minus S1P is a whole number of wavelengths lambda, n lambda. Okay. So now, okay, we're then saying whole number of wavelengths, hence S2P minus S1P is n lambda, where n is 0, 1, 2. Destructive interference or cancellation occurs whenever the difference in path length, which is S2P minus S1P, is a whole number of wavelengths plus half a wavelength. That is, S2P minus S1P is equal to n plus 1 half lambda, where n is 0, 1, 2, and so on. So those are the kinds of things that you actually need to take note of. So now we then have the following. So, right, let's continue. Let's continue. Right, and I want us to reiterate the notion of this particular drawing alongside depicts two sources, S1 and S2, generating identical light waves. Here is source 1 and source 2 generating identical light waves. The waves interfere at a point P. They interfere at a point P, but these identical light waves, which therefore interfere at a point P, on a screen at a distance x from a plane from the plane of the sources. Constructive interference occurs at P when the waves S1 and S2 are in step, which happens whenever the difference in path length, which is S2P minus S1P, is a whole number of wavelengths and lambda. Hence, S2P minus S1P is n lambda, where n equals 0, 1, 2. Okay. Destructive interference or cancellation occurs whenever the difference in path length, S2P minus S1P, is a whole number of wavelengths plus half a wavelength, which means S2P minus S1P is n plus 1 half lambda, where that is the case. Let's look at example 3.1, constructive or destructive interference. Two identical sources, A and B, are emitting radio waves of wavelength 0.8. Two identical sources, A and B, are emitting radio waves of wavelength 0.8. If destructive interference occurs at a point 1.6 meters from A, determine the smallest possible value of the distance from point B where destructive interference occurs. Destructive interference. So now at this point we have two identical sources, A and B. So in other words, there is a source A and then there is a source B. A source A and then a source B. And like we saw before, there's something special about these two sources because they are sources of radio waves. And these radio waves meet. They meet there. But these two identical sources, A and B, are emitting radio waves of wavelength 0.8 meters. If destructive interference occurs at 1.6 meters, so you're going to measure here the usual x, and you're going to call it 1.6 meters from A. Determine the smallest possible value of the distance from point B where destructive interference occurs. Where destructive interference occurs. Okay. So now the destructive interference therefore would mean that, okay, I want us to reason this out, reason this out, reason this out. Right, 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 right. So obviously, if this is a point C, you then are able to see that your BC, if the destructive interference occurs at the point there, you then say BC minus AC is N plus N plus 1/2 lambda, which is so BC minus AC. Okay. So now at this point, you'd see that you'd have the following. Determine the smallest possible value of the distance from point B where the destructive interference occurs. Destructive interference occurs when this is the case. That is true. The smallest distance is found when n is 0, which means that you shall have 0 plus 1/2. The wavelength itself is 0.8, and therefore the answer becomes exactly 0.4 meters. Therefore, the distance from point B is exactly what? Right, the distance from point B is exactly AC plus 0.4, and that would actually exactly be 2.0. Just check that. So obviously now, if the destructive interference occurs at a point 1.6 meters from A, 1.6 meters from A, right, determine the smallest possible value. So now this distance would therefore be AC plus 0.4, the distance. The distance from point B. Right, so you look at the distance from point B. Right, so we shall look at the distance from point B. the distance from point B. The distance from point B becomes exactly AC. AC plus 0.4. Right, so if then that is the case, you then have the AC, which is 1.6 meters from point A plus 0.4, which is 2.0 meters. So, okay, let's look at Huygens principle. Huygens principle. Suppose wave spread from S. W is a wave front. They spread from S, but W is a wave front. All points on a wave front are at the same stage or phase of their wave motion as the wave at the same instant. To find the new position W of the wave front a short time later, we use a Huygens principle. So to find the new position W of the wave front a short time later, we use Huygens principle. Huygens principle. Every point on a wave front acts as a secondary source. This is the principle, Huygens principle. You must always remember to state it. Every point on a wave front acts as a secondary source, sending out wavelets that move with speed of the wave. With the speed of the wave front at a later instant is yes, the wave front at a later instant is the surface that is tangential to these wavelets. So we have the following. We then have the following. We then have the following. Right. Okay. Huygens principle. Every point on a wavefront acts as a secondary source, sending out wavelets that move with the speed of the wave. Every point on a wavefront acts as a secondary source, sending out wavelets that move with the speed of the wave. The wavefront at a later instant is the surface that is tangential to these wavelets. The wavefront at the later instant is the surface that is tangential to these wavelets. Let us look at the next point. So in other words, you have a wavefront here, but there's another wavefront there at a later stage. And this wavefront at the later instant is the surface that is tangential to these wavelets. Okay, so we have the following. We would have exactly the following. We would have exactly the following. Okay. Okay, the similar ideas apply. Similar ideas apply whatever the shape of W the wavefront. For plane waves, the wave front is perpendicular to the direction of travel. Right, so now for plane waves, the wave front is perpendicular to the direction of travel. In the above examples, Huygen's principle has no particular merit. Um, Common sense tells us that to expect tells us what to expect anyway. It does become useful however, when considering some considering other aspects such as direction, refraction, diffraction, etc. Okay, so now we continue. Okay, so we continue. Right, so similar ideas apply whatever the shape of W, whatever we're saying similar ideas apply whatever the shape W or whatever the shape of the wavefront. So now for plane waves, the wavefront is perpendicular to direction of travel. For plane waves, the wavefront is perpendicular to direction of travel. In the above examples, Huygens principle has no particular merit. The direction of travel like this for the plane waves, you're able to see that this is the wavefront. Direction of travel is like this, but for plane waves, the wavefront is perpendicular to the direction of travel. This is the wavefront. It is surely perpendicular to the direction of travel because this is direction of travel, and that is the wavefront. They make an angle of 90 degrees there. In the above examples, Huygens principle has no particular merit. Common sense tells us what to expect. Anyway, it does become useful, however, when considering other effects such as reflection, refraction, diffraction, etc. All right. Okay. Note also that Huygens principle applies to all kinds of wave. Note also that Huygens principle applies to all kinds of wave, light waves, water waves, sound waves, etc. We can use it, for example, to explain how sound bends or diffracts around edges of a doorway. Thus, a listener at point P in the diagram can hear sound from the next room, even though she's not directly in front of the opening. Okay. Here's the listener at point P, and here's the doorway, and this person at this point is able to hear the sound. Diffraction of waves passing through an opening in a barrier. Passing through an opening in a barrier. So let us look at reflection, because before we were looking at Huygens principle. Let us speak about, so we've discussed diffraction. We've discussed diffraction. We use it, for example, to explain how sound bends or diffracts around the edges of a doorway. So diffraction of waves passing through an opening in a barrier. Reflection. AB is the advancing plane wave front which has velocity small v. So Now, then we have the following. Then we have the following. We have exactly the following. Okay, we continue. We look at this one. Reflection. Here is an incident ray. In this one is reflected incident reflection. Incident reflection in the normal. Yes. So we continue. We continue. Ah, we continue. We continue. Okay. Now we're saying AB, here's AB, is the advancing plane wave front, which has velocity v. AB, advancing plane wave front with velocity v. AB. AN, AN and CN are normals. Okay, rather, AN and CN are normals. Since the angle PAN, PAN and N and NAB, yeah, PAN plus NAB equal 90 degrees. And NAB plus BAC is 90 degrees. Then, right, then you have BAC, BAC plus PAN. They are both incident angles equals I. Similarly, the angle DCA, right, the angle DCA is equal to the angle NCQ, right, NCQ equals R. And these are the angles of reflection. Okay, each point on the surface from A to C successively acts as a secondary source as the corresponding point on AB arrives. In the time taken, T, from B to reach C, a secondary wave from A or radius AD to VT, which equals BC, has spread to D. The CD is the new wave front. Moreover, since the triangles ABC and ABC are congruent, Why? Then the angle of incidence equals the angle of reflection. That is, the angle of incidence equals the angle of reflection. This was stated without proof as the first law of reflection in your geometrical optics notes. The second law of reflection can also be justified by a detailed three-dimensional application of Huygens principle. Okay, let's discuss refraction very briefly. Let us discuss refraction very briefly. Okay, some of these things, let me see now. Let's discuss refraction very briefly. Okay, you see, I'm thinking about these things and yeah, yep. Okay, I'm thinking about these things here. I'm thinking about these things that are going on. I'm thinking about these things that are going on. I'm thinking about these things that are going on. Uh, right, we'll have to do this. We'll have to, yeah, we shall push now, but also see what we can do at 4. Okay, let's just push. And then we can also see what to do at 4 in the morning. Now, let's look at refraction. You have the angle of incidence and the angle of reflection. Now, AB is a plane wavefront, velocity V1 in the phase medium. Each point on the surface from A to C successively acts as a secondary source as the corresponding point on AB arrives, sending out wavelets with speed V2 in the second medium. Now, in the time t for B to reach C, a secondary wave from A, radius AD equals V2T, has spread to D. Right now, CD is the new refracted wavefront. Right, so let's look at CD. It's a new refracted wavefront. BC, it's V1T. So BC is V1T and AD is V2T. Has spread to C to D. CD is the new refracted wavefront. Okay. Using similar reasoning as section 4.1, angle BAC is the incident. Okay. And angle ACD, angle ACD is the angle of refraction. So let us look at this very carefully. So if BAC, right, if you're able to see BAC as equal to the angle of incidence, and ACD as being equal to the angle R. Thus, since BC is V1T and AD is V2T, which is the sine of the angle incident divided by the sine of the angle of refraction, must be equal to a constant. So the sine of the angle of incidence divided by the sine of the angle of refraction is actually equal to V1 associated with the angle of incidence and V2 associated with the angle of refraction, and this therefore equals a constant. Now the constant above is called the refractive index. The constant above is termed the refractive index of the second medium with respect to the first. The second law of refraction may also be established with the use of what we call Huygen's principle. Let's look at interference. But before we look at interference, the constant above is called what we call the refractive index. So you need to know that the refractive index is the sine of the angle of incidence divided by the sine of the angle of refraction. It is equal to V1 over V2, and this is equal to a constant. And this constant is called the refractive index. Interference. Young's double slit experiment. Young's double slit experiment. So you're dealing therefore with the source in S1, S2, overlapping region, interference fringes, schematic representation of double slit interference, monochromatic light from the illuminated slit S falls on slits S1 and S2. The sets of waves spreading from these slits are identical since they're both derived from the same original source, the illuminated slit S. Interference fringes are observed on the screen in the region of overlap between the two sets of the waves. Okay, good. We continue. We continue. But before I continue, I want us to pause to reason this Young's double slit experiment. You need to understand it, but also so that you can be able to do the questions. It is very important to look at that, the fact that this one is a schematic representation of the double slit interference light source and monochromatic light from an illuminated slit S falls on slits S1 and S2, right? So this monochromatic light, which is light of a single wavelength of frequency from the illuminated slit S, falls on slits 1 and S1 and S2. The sets of waves spreading from these slits are identical since they are both derived from the same original source. Yeah, the sets of waves spreading from these slits are identical. Yeah, the waves spreading from these slits are identical. Right, since they are both derived from the same original source, the illuminated slit S. Interference fringes are observed on the screen in the region of overlap between the two sets of waves. So you can see some what we call the interference fringes. Right, so now there are interference fringes that are observed on the screen, because now then you'd have that then there's going to be another source 1, source 2 that's going to be an apparent source. So this one now spreads like this, and this last spreads like this, and therefore there is an overlapping region of the interference fringes. Notice that interference fringes could be observed in any plane in the overlapping region. These fringes are therefore said to be non-localized. Compare these with the thin film interference fringes discussed in section 5.2. Geometry of the nth bright fringe at P. A distance x from the plane of the slits S1, S2 separated by distance d. Looking at figure 8, for example, d is the separation of the sources. Right, so d becomes the separation of the sources, and yn, the distance from the axis to the nth bright fringe, yn, the distance from the axis, right? This is the axis from the axis to the nth bright fringe. This is yn. on the screen. Suppose Q is a point such that S1P is QP. S1 S1P is equal to QP. Right. Then S2P minus S1P. Then you have S2P minus S1P is equal to actually S2Q. Okay. Yes. So S2P, which is this one, minus S1P is equal to this small difference here, S2Q. Constructive interference, that is the bright fringe, occurs when S2P minus S1P is equal to n lambda. Hence, we have that S2Q becomes n lambda. Now, OPC figure 8 is perpendicular to S1Q, hence the angle S1 is S2 S1 Q is equal to theta. Also, if X is much larger than D or Yn, S1 is approximately perpendicular to that. Okay, so that you have S2Q is D sine theta. Okay, I'm just reading through these so that you can just take note of the formulas here. Combining these two, because you shall be using them when you do the exercises. Combining these two expressions, S2Q above, we find that the bright fringes to okay. I think that these things are a bit a lot, so I think that we'll have to take a break and return at 4. But when you return at 4, we shall just do the exercises, and I think that that is the best because, yeah, it's lots of these things. It's lots of these things. I think that let's come back at 4. I'm gonna be here at 4. We shall do the exercises. We shall run through the activities like fast, 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 fast. I think that that is going to make the difference. Because now it's like half 1, you know. I suggest that we take a break. At 4, when we come back, we do the tutorials, those questions at the end. I think that that will be the best we can do. Because, yeah, it's time that we need to deal with, but we need to balance our time. So, yeah, I think let's take a break because I'm just looking at the things. There are too many. But when we return at 4, then we shall run through those activities. I think that that is going to save us a lot of time, you know? So that is what I suggest we do. That is what I suggest we do. That is what I suggest we do. Right. That is what I suggest we do. So now I suggest that we take a break and then we can return at 4. When we return at 4, we're going to do those questions to save time because our time is gone already. But if we rush a lot through them, we might finish them. You know, we might do a greater part from 4 to 6, something like that. And then the difference, you let me know when you're going to be free again. So let's do that. Let's just take a break now. And we shall return again at what time? At 4 a.m. I think that's the best. Yeah, that's what I'm thinking. You just have one now. I understand we started a little bit late, but yeah, let's relax a little bit and make sure we have energy to start at 4. I'm going to wake you up at 4. I'm going to buzz you on the phone. Right. So, yeah, let's take a break now. I'm going to be back at 4. Thanks so much for your time. I understand I'm just looking at the things. You need to relax a bit first before in the morning, you know. So thanks a lot for now. I'll see you at 4 a.m. I'll give you a buzz at 4 a.m.